Today we are going to do the nuclear physics. In this part we are going to learn about radioactivity, Geiger Counter, radioactive decay. First we'll talk about radioactivity. What is radioactivity? It is the ability of naturally existing heavy elements to transform its unstable nuclei to new stable nuclei by spontaneous emission of radiation. Radioactivity is a natural and a random process, and it is independent of the chemical compound in the element or any physical properties such as temperature, pressure or pH. Radioactivity is also called as disintegration or transmutation or radioactive decay. In nuclear physics, we talk about the changes that occur in the nucleus of atoms. So here onward, we are denoting a nucleus or a nuclei of an atom like this. This will be the chemical element, and as a superscript we write its mass number, and as a subscript we'll write its atomic number or the proton number. As examples for nuclei, there are radioactive nuclei like uranium 238 and 92 and thorium 238 90. These nuclei are naturally existing, so we call them natural radioactive elements. But there are certain nuclei that are formed by reactions that show radioactivity. We call them as artificial radioactive nuclei. So these are artificial radioactive nuclei. There are three main types of radiations that we are going to learn. One is alpha, beta and gamma. Out of these three radiations, alpha and beta rays are particles, but gamma rays are electromagnetic radiation. First, we will talk about the properties of alpha particles. An alpha particle can be denoted by 2 protons and 2 neutrons. Its atomic number will be 2 and its mass number will be 4. And also can be denoted by a helium nucleus. So when we take the charge of an alpha particle, an alpha particle is positively charged and with a magnitude of 2 times of the charge of an electron. The charge of an electron is 1.6 into 10 to the power minus 19 coulombs. So only thing is this is 2 times of that and also positive. And its mass will be equal to 4 times U. U is the unified atomic mass unit. That is the mass of 1/12 of a 12 carbon atom, which is in magnitude equal to 1.66 into 10 to the power minus 27 kilograms. When we take the speed of an alpha particle, it is only around 6% of the speed of light. Which is equal to 3 into 10 to the power 6 meters per second, the speed of light. And its kinetic energy is around 6 mega electron volts. And when we consider alpha particles, they have the highest ionizing power In fact, it's very high. They can ionize any particle when they collide with them. And alpha particles are having the largest nuclei, so they are comparatively heavier than other types of radiations. Therefore, it will have a less penetration ability. For example, it can penetrate air for about like 3 to 10 centimeters. It can penetrate through an aluminium sheet or a paper of thickness less than 0.1 millimeter. So it can also be stopped by a cardboard. So their behavior in front of electric and magnetic fields would be exactly similar to a positive charge, which behaves in an electric or magnetic field. Emission of an alpha particle is called the alpha decay. And when an alpha particle is emitted from a nucleus, we call this the parent nucleus. The daughter nucleus will be having a mass number which is 4 less than the parent nucleus, and also an atomic number which is 2 less than the parent nucleus. Properties of beta particles. Beta particle can be denoted by with a mass of 0 and a charge of -1, or like this. So they are also high speed electrons with a speed which is about 98% of the speed of light. And they have a high kinetic energy, but comparatively to alpha particles, their kinetic energy is low because alpha particles are having a higher mass than beta particles. Beta particles are emitted from the nuclei which have a higher number of neutrons. So a neutron will be converted to a proton plus a beta particle, which also liberate another type of particle called a neutrino plus energy. So we need to take the balancing of the mass and charge. Neutron is having a 1 mass and 0 charge, but proton is having the 1 mass and a positive charge, and the beta particle will have no mass and -1 charge, so it balances. When you take a neutrino has the same mass of an electron or a beta particle, and it is a chargeless particle or electrically neutral. So this type of particle emits to balance the momentum when the beta particle is released. So inside a nucleus, a neutron will be converted to a proton, and an electron will be emitted with a kinetic energy, and to balance the momentum, the initial momentum will be 0. So to balance the momentum, an equal mass particle will be ejected to the opposite side. As beta particles are lighter and fast moving compared to alpha particles, their interaction with other particles or atoms during a very short time period is less. So their ionizing ability is low compared to alpha particles, but they have a higher penetration ability than alpha particles. They say that a beta particle with a maximum kinetic energy can travel in air up to 500 centimeters, and it also can be stopped by an aluminium sheet of thickness about 3 millimeters. Example for beta emission, if we write during a beta decay or beta emission from a nuclei of mass number A and proton number Z, we can observe that the mass number will not change, and a new nuclei will be formed with a proton number which is one more than the parent nuclei, and a beta particle will be emitted with a neutrino and energy. So usually in questions they don't expect us to write the neutrino part, but it's best to write it. As an example, when we consider the radioactive 14 carbon isotope, it will show a beta decay by forming the nitrogen nuclei, 14 nitrogen nuclei with beta particle and a neutrino and energy. Next, we're going to talk about the properties of gamma radiation. Gamma rays, they are electromagnetic radiation, and they can be denoted by this, as they don't have a mass or a charge. They are massless and chargeless particles, or simply they can be represented by gamma. After an alpha decay or a beta decay, most nuclei exist as an excited state. So therefore they emit very short wavelengths of electromagnetic radiations called gamma rays to reach their ground state. When compared to the energy, the photon energy of visible light, which is about 1 electron volt, the photon energy of gamma rays is considered very high. It's around 1 mega electron volt to 1 giga electron volt. Unlike the emission of alpha particles or beta particles, the element corresponding to nucleus does not change due to gamma radiation. So as an example, if we write the nuclei X with mass number A and proton number Z, which is excited, comes to ground state with the same mass number and the proton number, with liberating a gamma photon. So comparing the ionizing ability of gamma rays with alpha and beta particles, the ionizing ability is negligible in gamma rays, but their ability to penetrate is very high compared to both alpha and beta particles, and gamma radiations have a very high energy than both alpha and beta particles. So it can penetrate metal plates with thickness of few centimeters, and their intensity will decrease about 10% when passing through a lead sheet of thickness about 4 centimeters. Gamma rays are electrically neutral, as we can see. They have no charge, so they are not deflected by a electric or magnetic field. So as an example for gamma radiation, we can write boron 12 5 will give carbon 12-6 and a beta particle. So the carbon 12-6 nuclei will be excited here. So secondly, it will come to ground state by releasing a gamma radiation. When we consider a magnetic field in a direction into the paper, and if we send these three type of radiations, alpha radiation, gamma radiation and a beta radiation, starting from these points, we know that alpha is with +2 charge, beta is with -1 charge and gamma is with 0 charge. So as gamma particles are having 0 charge, they will not have any deflection if we project a gamma photon towards this side. So it will move undeflected through a magnetic field. And when you take the beta radiation, we can observe that it will be the most deflected, as it is having a less mass than alpha particles. And when we consider alpha particles, they will be slightly deflected because they are having a higher mass than beta particles. Next, we're going to talk about natural radioactive series. When we consider some naturally existing heavy metals, they convert into new elements by spontaneous emission or disintegration of alpha particles, beta particles and gamma rays, which is called radioactive decay. Also, sometimes they undergo repetitive disintegrations, which is called radioactive series, and in this case it is natural. As examples, there are 3 such naturally existing radioactive series. One will be the uranium series, in which uranium nuclei with 238 mass number and 92 proton number, and after repetitive disintegrations it will finally form the nuclei of 206 lead. And in thorium series, which begins with 23290 thorium nuclei and finishes with 20882 lead isotope. And the actinium series begins with actinium 227 and finishes with, after repetitive disintegrations, 20782 lead isotope. Next, we're going to talk about artificial radioactivity. So for some elements that are not naturally radioactive, we can induce radioactivity by striking with some atomic particles for a particular element. So for example, we take 19 fluorine nuclei and we strike it with helium 4 nucleus, and then we can obtain an artificial radioactive element of 22 sodium, and a neutron will be emitted. And when we take this artificial radioactive element, we can observe that it will decay into neon 2210 by emitting a special type of particle which is called a positron. So a positron is emitted only during artificial radioactive decay. So a positron has a mass of an electron, which is rather massless, and a charge which is equal to the magnitude of the charge of an electron, but it is positive, and it is exactly the same as an electron, but the charges are opposite. This is also called a positive beta decay. Next, we're going to talk about the Geiger Counter, which is a common device used to detect radiation quantitatively. It can also identify alpha particles, beta particles, gamma rays, and X-rays. So this is a diagram of a Geiger counter which contains a cylinder, a metal cylinder with a thin mica window and a metal frame with an anode wire containing a glass pebble at the tip and a cathode which is connected to the metal cylinder. So the cathode will be the metal cylinder, and it is connected to a high power supply of around 450 volts, and inside the cylinder it's filled up with argon gas and a small amount of chlorine gas. The outer shell will be earthed. So when a radiation is fallen onto this thin mica window, alpha particle, beta particle, gamma ray or X-ray photons, they will pass into the cylindrical space, and after they enter, they ionize the argon atoms, forming electrons and argon ions. The formed electrons will be attracted towards the anode, which is in the center, and the positive ions will be moving towards the cathode. So if we draw a diagram to show the electric field between the cathode and anode, if this is the electric flux lines between the anode wire and the cylindrical cathode, anode which is positive and cathode which is negative, we can see that the electric field intensity about the anode is very high because the number of flux lines per unit area is greater, but the electric field intensity towards the cathode will be less. Accordingly, when electrons are emitted after an argon atom collides with a type of radiation, the electrons emitted will be moved towards the anode with a very high speed, but argon ions or positive ions, they move towards the opposite side but with a lesser speed due to the less electric field intensity towards the cathode, but electrons are moving with a higher speed. An electron formed can also produce secondary electrons by colliding with argon atoms. So there will be two electrons formed, and the argon plus ion will be moving towards that side if this is towards the anode. And furthermore, electrons can form new electrons. This is called secondary ionization. So at the same time, the kinetic energy of these electrons which are moving towards this side will be gradually increased. And at the same time, the positive charged particles closer to these electrons will also increase. So now a large number of electrons are moving towards the anode with a very high speed. So once these batch of electrons are sent to the anode, a current pulse, we say that a current pulse is sent to the anode, and it will move through the external circuit and will be detected. There are a large number of argon ions inside the tube still, which help in reducing this electric field and prevent the formation of another pulse through the anode. And later the argon ions will be neutralized by the halides present in the gas. The current pulse will be passed through the circuit and into a scale counter or a rate meter, which will identify the rate of insertion of a particle or photons and also its properties. And we saw a small pebble that is attached to the anode wire, to the tip of the anode wire. This is to prevent the formation of electric sparks due to the point discharge between the tip of the anode and the cathode. Now we're going to focus on the laws of radioactive decay. What is radioactive decay? When we take a mass, or rather a certain number of nuclei of a certain radioactive element, after a t period of time, we can observe that the mass or the number of nuclei inside this radioactive element is lesser than the previous value. And after a certain more amount of time, we can observe that the number of nuclei is further lesser than the previous value. So this is called the radioactive decay. That is, the number of nuclei inside the radioactive matter decreases with time. So there is an equation. So there is a law for radioactive decay. It is said that if n is the current number of radioactive nuclei in the sample, and if delta n over delta t is the number of disintegrations per second, it is found that the number of disintegrations per second is directly proportional to the amount of, or the number of nuclei initially present in the sample. So we can write the law of radioactive decay as the number of disintegrations per second is directly proportional to the number of radioactive nuclei initially in the sample. So as this disintegration is negative, as the number of radioactive nuclei are loosened from the initial sample, we write it as negative disintegration. And it was found that this is equal to a constant. It was found that this can be equaled with a constant lambda, which we call the radioactive decay constant, measured in per seconds. We take this negative sign towards this side, negative, yes. This is the law of disintegration in terms of number of nuclei existing in the sample and the number of disintegrations per second. If we consider, for instance, the number of radioactive nuclei in the sample at t equals 0 is equal to n naught, and after a certain t amount of time the number of radioactive nuclei present in the sample is n. We'll try to build up an equation. We can write the previous equation, and by using a mathematical process called integration we can find an equation to represent only using these values, where bio students do not need to know the full integration process. So after integration we can obtain the equation n is equal to n naught e to the power minus lambda t. So this can be also written as natural log n over n naught is equal to minus lambda t. As this represent an exponential graph, that's why the exponential sign is here. So for bio students I'm telling this is more similar to log, but as in logarithms we take the base as 10. Here it's a bit different. So for example in logarithms of base 10 if we take log 10x is equal to y, it means that x is equal to 10 to the power y. So you know, so in here in ln e, in exponentials, ln e x means if it means ln e x is y, it means that x is equal to e to the power y. Okay, so when we convert an exponential value to a log value, we can simply, if it is this particular value, we'll say y. If we want to convert this to a log value, we can simply just multiply it by 2.303 and then it will become the log value of y. So this will be needed to convert it to a normal, more preferable value. So we'll again go to the equation we obtained, which is equal to n is equal to n naught e to the power minus lambda t. So this t is the elapsed time, or the time which is allowed to disintegrate. So when you take lambda, which is the decay constant or the radioactive decay constant, it is actually a characteristic of the relevant parent nucleus. So it depends on the parent nucleus and it is constant to a specific parent nucleus. Next we're going to talk about the half-life. We represent it symbolically as T half. So what is half-life? When we take a radioactive sample of n number of nuclei, the time taken by this sample to become the number of nuclei n by 2 is called the half-life. Okay, so the half-life of a radioactive element will be a constant for that radioactive substance. So if we substitute to the equation that we know, which is n is equal to n naught e to the power minus lambda t. We know that the number of existing nuclei is now equal to half of the initial number, so we can write n by half is equal to n into e to the power minus lambda t. We can write half is equal to e to the power minus lambda t. So to remove this minus of the index form, I am taking this e to lower side. Half is equal to 1 over e to the power lambda t. Now it's positive. Now I can also write as 2 is equal to e to the power lambda t. So here actually e to the power t is actually e to the power lambda t half, because this is the half-life. So according to this equation, if the power of a E value can be represented like this, we can write it as the power can be subjected, and this can be written as in natural log form. So I'm going to do that when this power will be replaced as ln e2 will be equal to lambda t half in lambda into t half. So next, using this equation, I am going to remove this exponential and convert it to log, which is more preferable for calculations. So removing this ln e, I am going to multiply it by 2.303 log 10, and I'm writing lambda t half. So after simplifying this value, I'm getting a value of 0.693 equal to lambda t half. So I'm getting an equation for t half, which is 0.693 divided by lambda, or the decay constant. So this is the equation you need not to derive, but you can memorize it and directly use in calculations. If we draw the graphical variation of decrease in the number of parent nuclei, we can get something like this, which is an exponential type curve. And initially there was a naught amount of parent nuclei, and after it will get exactly half in naught by 2, and the time taken to that, which is represented by the x-axis, is equal to t half, which is the half-life. And we can see this number of nuclei will be exactly halved in naught divided by 4 with an equal amount of time, which is 2t half. After 2 half-lives, this number will be halved again. It will never touch the time axis. Now if you draw the graphical variation of the increase in the number of daughter nuclei, it will be something like this. Initially the daughter nuclei is 0, so it will start from 0, and it will increase exponentially, and yes, it's this will be the N0 value. This is N0 divided by 2. So it will reach this number of nuclei, which is half to the parent nuclei at a t-half time period, and it will reach a 3/4 of the number of parent nuclei at 2 times the half-life, and it will never touch this axis or the exact number of parent nuclei. Next we'll talk about activity. Activity is the rate of disintegration, or we can also define activity as the number of disintegrations occurring per second of a sample. So we can write activity denoted by A as negative delta n by delta t, as activity is represented as a positive integer, and also from the previous equation we can write activity is equal to lambda n. Here n is the number of radioactive nuclei present initially in the sample, but here n is the number of disintegrations per second. Okay, so this lambda is the decay constant. The SI unit of activity is a becquerel. So 1 becquerel represent 1 disintegration per second. Also, when we consider the previous equation, n is equal to n0 e to the power minus lambda t, we can multiply each side by lambda, so that it will be n lambda, n0 lambda to the power minus lambda t. So as you know, n lambda is equal to a. This is the activity of the sample after a certain t amount of time, and this is the activity of the sample initially present. So we can derive this equation, which denotes the activity of the sample after a t amount of time.
Thanks for watching. Hope this video was helpful. If you did, make sure to give it a thumbs up and leave a comment below. Subscribe us and click the bell icon for more videos like this.